All right, welcome to lesson 1.1 as we actually start the ideas of calculus. We're going to look at two concepts today that are very important because you see it throughout the entire calculus course. So make sure you have a good understanding of these concepts before moving forward. Now, one of the concepts we'll talk about is limits. Yes, now informally, a limit really is just a y value which a function approaches, and here's the key word, approaches, as x approaches some other value. So in the past, we've always said, what happens when x equals to something? Now the question is, what happens to the function when x approaches something? Now, you've seen the notation before in one of our lessons from Unit 0, but this is the formal notation for limits. The limits as x approach to a number c, and this c, of course, is an x value. And what they're saying is, what is the corresponding f of x value or the y value? Well, that's L. So L represents the y value. Okay? So what does this mean again? Here are the key things. As x approaches c, the y value or the function value approaches the y value, which is equal to L. Okay? So let's look at some of these examples here. Okay, I've got this nice graph, scary graph for a function of f of x. But nonetheless, we have these questions about limits and then function values. So let's look at number one. Limit as x approaches negative 4. So really what I'm saying is, look, I'm moving along the curve and I'm coming, and approaching negative 4. If I'm coming from the left side, I'm approaching negative 4, and I'm coming from the right side, I'm approaching negative 4. What is the corresponding y value that I'm approaching here? And if you said the answer is 1, you are correct. Okay? Now, what about number 2? X approaching negative 1. So we're looking at what happens when it approaches the value of negative 1. So if I'm coming from the left here, woo! Oh, and from the right-hand side, woo! Notice they both converge onto what particular y value? Once again, I'm not saying equal to, but getting closer and closer to. If you said 4, you are correct. Okay. Now, if you said, oh, the y value is 1 here, that's not the limit value, but that's actually the function value. That's number 9 here, okay? So that's equal to 1. See the difference between the two? Okay. Limit, meaning approaching to, function value equaling. All right, number 3. X approaches to 2, getting closer and closer to, yep. If you said 1, that's good. And then now if I choose number 4, the limit as x approaches to 3, I'm saying let's see what happens when it gets closer and closer to 3. Well, going from the left-hand side, it looks like, whoa, it's going really far down. And coming from the right-hand side, whoa, it's also going really far down. So what's really, really far down? Well, you can consider that negative infinity. Or some people use this idea of DNE. Now, DNE means does not exist because it's not really a value, right? Negative infinity, how do we classify that? Well, it's just something really, really big negatively. So sometimes people use this notation DNE. Okay? DNE stands for does not exist. Okay? And let's take a look at number 5 now. The limit as x approaches to 5. So now I'm saying, okay, let's approach 5. Coming from the left-hand side, it seems to be getting closer and closer to this value. Coming from the right, oh, it seems like it's approaching a different value. So if the two different values from the left and the right are different, well, guess what? That means that the limit at the particular value also does not exist. Okay? So these are a little bit tricky, but nonetheless, those are the answers. Now, we already did mention earlier about how the limit and the function values are a little bit different. So I did number 9 for you already. Can you go back and finish off number 8, 10, 11, and 12? Okay, so go for it. F of negative 4. There's that solid dot right here at 1. F of 2. Notice that there is no solid dot anywhere. So f of 2 is just undefined. Okay, not there. Okay, or if you want to use that idea of does not exist, also doesn't exist, right? Not there. F of 3, well, that's an asymptote, so once again, undefined. or if you want to use the idea does not exist, that's fine. And then how about f of 5? So at 5, I have an open dot and the solid dot. And if you said, oh, I should quote the solid dot for the actual value, you are correct. Okay? Now, can I ask you to, and I know I did this earlier, I should have that first because this is 6 and 7, but I got too excited when I saw the function values. But remember when we looked at the limit as x approached to 5? Okay, so that's right about here again. Let's focus on this again. Remember how I said coming from the left, we had an answer? That was -1. Coming from the right, however, we had a different answer. That was 2. Well, how do we show that with notation? Well, we can with one-sided limits. So for number 6, when I say the limit as x approaches to 5 from the left, that's the 5 minus, okay? So this is really 5 from the left. And the particular value here would be -1. And for number 7 here, yes, that is 5 from the right, okay? 5 from the right side. And in this case, the value was, 2. All right? And I want you to notice here, okay? Because, or I'll say since, the limit at x approaches to 5 from the left of the function does not equal to the limit as x approaches to 5 from the right of that same function. Therefore, the limit at, okay, the limit at, or the limit when x approaches the actual number 5 does not exist. So in order for a limit at a number to exist, the limit from the left must equal to the limit from the right. Okay? That's a key statement that you need to know. All right then, so that's the introduction to this idea of limit with a graph. I'd like to continue our studies today to talk about this idea called continuity. And that looks like the word continuous, yes. So informally, it's really a function is continuous where it can be drawn without lifting a pencil, meaning I can get a nice, smooth, connected curve. Well, that's not a function, but even corners like that, that's okay, as long as I don't have to lift up my pencil. Formally, though, a function is continuous where its limit and the function value are the same. So let me write down notation for you here, and you should do this too, okay? What I'm saying here is that the limit at some value of a of the function, or its limit, right, and its function value, f of a, they are both the same. Okay. Now remember, for the limit to exist from above, we need to ensure that, yes, the left limit and the right-hand limit are the same. Okay? And that's why, for the proper definition, the function of f is continuous at an x value c if and only if the limit from the left equals the limit from the right, which equals the value of c. So if you want to actually change your notes to make it more coordinated, I guess I should have used c, not a, but c. C. Okay? So really, these 2 points point to this fact that the limit must exist. Okay? Now, in this course, we will work with 3 types of what we call discontinuities, things that have a break. Holes are places where there's a discontinuity. Vertical asymptotes are definitely a place where you have a discontinuity, and jumps or breaks. There is a 4th type of discontinuity that we might see, but very rare. It's called an oscillating discontinuity. And to investigate this, I'd like you to look at this lovely function and look closely to see what happens at x equal to 0. Okay? So if I ask you now to take a look at your function or your calculator, make sure you're in radian mode again. Okay, we're going to type in sine of 1 over x. So sine 1 over x. Okay, and this time if I just press standard graph, you'll see this lovely thing. And you're like, okay, nothing really special there. But I like us to focus in close to 0. Okay, so I'm going to zoom in at the point 0, 0, so I'm going to press enter now. And maybe you can see more things there. Oh, interesting. Okay. Maybe you can think, oh, it does look like it's getting closer to 0. But let's zoom in one more time. Okay, let's zoom in one more time at 0. Press enter again. Whoa, 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 whoa. Hey, looks like it's still 0. Okay, let's try one more time. And if you keep zooming in at 0, you will see that, it's not actually approaching 0 anymore. Yeah, it's going up and down, up and down. You see, that's why we call it oscillating. And therefore, in this case, what is this actually equal to? We don't really know. Okay? So therefore, this is a discontinuity as well. There's really no value at 0. All right? We'll talk about more of that later on. All right, back to our notes, example number 13. Can you look at the discontinuities of that graph from above and tell me what x values you find discontinuities? Yes, I think you can see one here, a whole ding at -1, ding at 2, ooh, an asymptote at 3, and some jump at 5. So there are 4 places where there are discontinuities. X equals to -1, 2, 3, and 5. Now, we can also classify these discontinuities. We can classify them as removable or non-removable. Now, removable ones occur when the function has a limit, okay? Really what I'm calling a hole in the graph. Where non-removable ones occur when the limit of the function does not exist. And those are the ones where you have a big jump or a vertical asymptote. So now look back at example number 13. Out of those 4 choices, -1, 2, 3, and 5, which of these discontinuities are removable? Meaning you can plug it up, or there's a hole. And if you said x equals to -1 and 2, you are correct. Good. Okay, so we've done a lot of visual graphing stuff. What I'd like to show you next is looking at actual functions. Now, notice that at x values where a function is continuous, right, when the function is continuous, the limits are actually the same as the value of the function. So the limits can really just be found by using direct substitution. So in this case, 3x squared plus 2, that's a parabola. We know it exists everywhere. There's no breaks. So really, if I want to find the limit, all I need to do is just plug in the value, 3 times 3 squared plus 2. That's 27 plus 2. Boom! The answer is 29. Okay? And I know this is equal to 3, but the limit is also the same value as when it's x is equal to 3. Now, for number 16, you may be thinking, oh, wait. There's a possible problem. X cannot be -1. True. But remember, I'm looking for, in this case, the limit as x equals to 1. And at 1, this function is continuous, so I don't have to worry about my non-permissible value. Once again, I can just directly substitute this in. So here we go. 1 squared plus 1, 1 plus 1, lots of 1s. That's 2 over 2. That's also equal to 1. And finally, the same thing, this cosine function we know is a nice periodic function that is continuous. So I just have to plug this in now. Cosine of this becomes what? 2 pi over 3. And this is where hopefully you remember how to actually find this without a calculator. 2 pi over 3 is in quadrant 2. We have here a reference angle of pi over 3. Hopefully you can see that the diagram I draw 2 pi over 3, what is it? This is 1, and I believe this is root 3, negative. And so now if I were to evaluate, cosine is x over r. How about -1/2? Happy? Okay, so nice and easy when it's continuous. We can just directly substitute in the values. But what about a piecewise function? These might not necessarily be continuous everywhere, so how do we go about doing the limits for these functions? Well, let's take a look at some examples here. Number 18 says if I've got f of x, and it's actually two pieces, it's 4 minus x when x is less than or equal to 1, and it's 4x minus x squared when x is bigger than 1, then what actually is the limit as x approaches to 1? Now, we can't just go blindly and plug this in right now, because we're not really sure what happens at 1, because there are two separate pieces. The breakpoint just happens to be at 1. So before you answer this, you better answer the following. Can you figure out the limit as x approaches to 1 from the left? Yes. To the left-hand side. Ooh, out of batteries. That's not good. And then can you also figure out the limit as x approaches to 1 from the right? And I want you to do that first before going and evaluating the limit as x approach to 1. So while I get some energy into this computer, you do this. So once again, ask yourself then, what is the limit as x approach to 1 from the left? Well, from 1 from the left, I have to plug it into which particular equation? 1 from the left? Yeah, 4 minus x. So 4 minus 1 gives us 3. Okay. Now, how about 1 from the right? So I'll plug it into the one that is bigger than 1 yet. So that's 4 times 1 minus 1 squared. That's also equal to 3. Good. We now know that the limit from the left is equal to the limit from the right. So therefore the limit at x approaches to 1 then must be 3. Beautiful. Okay, I'm going to ask you to do number 19 now, yourself. Try it, then come back and check your work with me. Did you think I was going to give you the answer so fast? I'm going to make you wait a little bit longer. Did you think that was 2? Did you calculate the limit from the right to be equal to 1? Uh-oh, this time they're different. So they're different. Yes, it does not exist. Good. Good. Now, for number 20, how about limit as x approach to negative 1? And you're thinking, do I have to go and do this again? Negative 1 from the left. Negative 1 from the right. Now, I guess you could, but notice you're going to actually plug it both into the same function. So you don't really need to actually do this left and right limit. This is just using direct substitution once again, because we know it is continuous at x equals to negative 1. And that, of course, just equals to negative 2. Okay, you would have got the same thing here, right? Negative 2, and that's why it exists 2. Okay. Finally, let's throw you some weird function. Okay, AP calculus, they throw you some weird stuff. So you might not have seen this before, but this is called the greatest integer function, or also known as a floor function. Sometimes we call it a step function because it looks like steps. Okay, the notation for this is looks like absolute value, but it's not. Okay, and really what I'm saying is the greatest integer function requires you to find the greatest integer less than or equal to x. So if I said, what's the greatest integer less than or equal to 4.5? You say the answer is 4. What is the greatest integer less than or equal to 2, you'd say? The answer is 2. The greatest integer less than or equal to, less than or equal to, I don't know, let me think now, 0.2? Yeah, that's 0. What about this one? The greatest integer less than or equal to, how about negative 1.2? Don't say negative 1. Think about here, negative 1.2, that's right here. Don't say negative 1. The greatest integer less than or equal to that, yes, it must be negative 2. So knowing this then, can you find the following limits here? At x approaches to a half, visually half is here, so you know that it is continuous. The answer is 0. But what about at 1? Well, at 1, notice, it looks like there's a jump, so therefore definitely it does not exist. But if you want to prove it, you can say that the limit from x approaches to 1 from the left of the greatest integer function, well, that equals 0. Yet the limit as x approaches to 1 from the right is equal to 1, and that is why then the limit at x approaches to 1 then does not exist. Okay, that's it for lesson 1.1. It's time for you to go and practice, practice, practice.